Welcome to Modeling, Not Programming, AMPL's model-based optimization tutorial for Informs Virtual 2020. In this presentation, I will begin with just an overview of optimization and its role in analytics. Optimization can mean many things, and I want to focus on what we'll be describing here. Then the main part of the talk will be a comparison of different approaches to optimization, uh, generally one that involves a more modeling approach and one more programming approach in different aspects of optimization applications. And then I'll conclude with some slides on case studies. So what is optimization in analytics? It's typically there are large numbers of decisions that need to be made, thousands to over millions, like the number of items to be shipped of each kind in each time period to each place, that sort of thing. There's an objective of minimizing or maximizing, something like cost or profit. And there are many constraints on the variables that restrict the values that they can have in a reasonable solution. Typically, there might be only 10 or 20 distinct types of constraints, but there are a very large number of each type, each of them involving just a small subset of variables. And finally, the problem that these things define is solved repeatedly with different data and with significant variation in the solutions. So there's no easy alternative to finding a way to solving these problems over and over again as the scenarios change. So then, why does optimization look that way in analytics? Well, it's because it is very widely applicable that way. So that paradigm of optimization is usable in many circumstances. And I've just listed current AMPL users here. And they range from energy to transportation to finance and just really just about any large scale kind of endeavor. And so let me now describe how do you do optimization, okay, if you're in one of these applications. And the steps are pretty straightforward. You start off by communicating with a client that has some difficult problem that involves potentially minimizing costs or maximizing profits. And you build some model or method that describes it, and you prepare some data scenarios and solve some cases. And then you can analyze the solutions and report some results. And then what do you do with those results? Well, this is what makes things more interesting as you take them back to the client, and typically the client finds fault with them. And so you have to discuss, well, what did they really want? What's not quite right about these solutions? What unknown constraints are they still violating? And then you go through this again. And typically optimization development is this whole cycle. It goes on repeatedly until you get something that can be used in a practical way. And it's this cycle that really influences the way that you choose optimization to do optimization in practice. So if you're a practitioner, because you need to do this cycle, you need to get the cycle done quickly and reliably and get some results before the client loses interest, because most of the early times through this cycle, your solution doesn't look so promising. And then you need to deploy that solution effectively for application and make updates as the situation changes over time. Now, this is a talk about optimization software, so we can also ask what are the goals for optimization software. And here we want software that will promote fast prototyping so that we can do this cycle quickly, but at the same time support integration with application systems and facilitate maintenance over the long term. So now let's look at the main part of the presentation. I'm going to consider optimization at 3 different levels, and each level I'm going to contrast 2 different approaches, one of which is more of a programming approach and one of which is more a modeling approach. And I'm going to argue that there are clear advantages to using a modeling approach in many cases. So first, I'll start off with just approaches to optimization. And there are 2 that I'll contrast. One is a method-based approach where you program a method or an algorithm for computing solutions. And the other is what I call a model-based approach where you formulate a description of the desired solutions. So you can see one is definitely more programming oriented and one is more modeling oriented. And in order to show the difference between these, I'll use a simple example. I call it supply chain optimization. It's really a simple network kind of flow problem. The motivation is to ship products efficiently to meet some demands. And you have this transportation network. I just have a drawing of some possibility there. And there are locations represented by circles and links between locations. And the supplies come in at these green arrows and demands have to be met at these red arrows. And you're required to observe certain capacities on these links. And also there are certain shipping costs that you incur when you ship along them. So then what you need to decide is how much of each product to ship on each link. So you see there are a large number of decisions, which is what we expect in an optimization problem in analytics. And we want to keep the shipping costs low. That's our objective. And we want shipments on each link to respect capacities. And at each one of these locations, we want the supplies and demands and the shipments to be in balance. So now given this problem, I can consider like how each of the two approaches might deal with it. So a method-based approach, you would program a method to build a shipping plan. A method tells you how to compute a solution. And so there are various ways you can do this. You could take an order-driven sort of way where you develop rules for how to meet each order, and then you piece them together until you have a shipment plan. Or you can take a route-driven approach where you find a good route from an origin to a destination and fill it up as much as possible, then find another good route and so on until you've filled them all up. And then once you've got this basic framework, you can refine it in many ways. You can enhance it by ordering the way that you consider your orders or your routes. You can improve the initial solution with various exchanges, and then there's been much study of all sorts of concepts for making more sophisticated improvements in any solution. You could even try to incorporate some aspects of optimal algorithms, although your chance of actually coming up with a completely optimal algorithm for some particular problem like this are not great. Okay? But there's lots you can do. The people have studied this for some time. And let's contrast that now with a model-based approach where the idea is to formulate a minimum cost shipping model, which is basically a description of what the solution ought to satisfy. So we identify the amount shipped as the decisions or variables. We specify the feasible shipment amounts by writing constraints or creating equations. We write the total shipping cost as some sort of summation over variables, and then we collect all the data. Okay? And once we've got that together, we've got a description of what we want, and we've got some data to try out. Then the second part of this is that we send all that to a off-the-shelf solver that computes solutions for a very broad classes of problems. And so there are really two parts to this. One is to formulate a description of what you want, and then send to a solver that knows how to deal with things that are described in that way, a very general purpose solver. And you'll notice that we didn't do any programming up here because we just made a description of what we wanted. And we didn't do any programming here because we used an off-the-shelf solver that's already been programmed by experts. So we didn't have to program anything specifically for our problem there either. And let me just show what a formulation would look like for this particular example. There'd be a description of the sets of products, locations, and links which define the network. And then three kinds of data. There's capacities, there are supplies or demands, and there are costs per unit of shipments. And so we just find that all in a abstract way there, and then we can describe in very concisely what the objectives and constraints are. First, we say that our variables there's one variable for every product shipped from each location to each other location in a link. And then the objective is just a sum of costs of all the shipments. And there are two kinds of constraints. One is that shipments are less than or equal to capacities, and the other is a balance constraint that shipments in and out must balance supplies and demands. And that's the whole description of the model. And so then which of these approaches would you prefer? Well, for a simple enough problem, any approach looks good. I have to say that 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 if only I could keep it this simple, then you could convince yourself that either a method-based or a model-based approach of any kind works pretty well. But the thing is that models aren't so simple, and this application development cycle that I described earlier ensures that every time you go around the cycle, more complications will be introduced. And it's these complications that really influence what it is you're going to end up doing. So, so complications could be things like additional restrictions, fixed and variable parts of the costs, minimum size of shipments, limits on the number of links used. Each of these will have additional data that go with them. And when I put in these complications, that will affect the approaches. So what does it do to the method-based approach? Well, you have to revise or rethink your solution approach and update or re-implement your method. And in this particular case, the trouble is that those additional complications have made the shipments more interdependent. And good routes are now harder to identify, improvements are harder to find. So you have more work cut out taking this approach. In general, even small changes to a problem can necessitate major changes to a method and its implementation. And every time there's a problem change, you have more method development. So this really is a challenge here. Problem changes because of that cycle are frequent. Now, method-based, what has to be done? Well, I have to update the objective expression, formulate some additional constraint equations, and send back to the solver. So basically, the challenges are that I have to add new variables and expressions to represent the fixed costs and some new constraints to impose shipment and ARC use limits. But in general, the formulation does tend to get more complicated, but a new solver type or options may or may not be needed. It's easier to update formulations than methods, and a few solver types actually handle many formulations. So the challenges are not as daunting here when you have to go back and change your formulation as when you have to go back and change your method. And in this particular example, I've just put in red the only things that change. There's one new kind of variable. There's an extra term in the objective for the fixed costs. There's a slight change to this constraint and two more constraints for these two more restrictions that have been put in. And that's it. So then it turns out that this can be sent back to the same kind of solver. So that's the argument for the model-based approach to optimization. But now we can go further and ask, well, what are the approaches to model-based optimization? And it turns out we have two there as well. And I have to say that I've glossed over an important part of model-based optimization, which is that of translation between the two forms of the problem, because I still have both my model and I have the solver. So I have a modeler's form, which is my symbolic description. That's that mathematical description that I gave a few slides back. But there's a solver's form. Those off-the-shelf solvers want some explicit data structure that they can compute with because they're basically number crunching programs. And you have to get from one form to the other. And there are two approaches to that, to translating between them. One is a programming language approach. Write a computer program to generate the solver's form, given your knowledge of the modeler's form. And there's a modeling language approach where you write the model formulation in a form that the computer can read and translate automatically. Now, I'm not going to say anything more about these two approaches because the modeling language approach has pretty much won out at this point. Has become the standard way of doing things. And so from now on, I'm going to assume that we're going to take the modeling language approach here. And now I'm going to ask, well, what are the approaches to modeling languages? And that's the third part of this presentation. And again, there'll be two approaches and programming will come back. So what I'm going to consider in particular are algebraic modeling languages, which are designed for the formulations that I showed on my slides, which are so-called algebraic formulations. They use algebra-like summations and arithmetic operators and so forth. And these have proved to be an excellent fit to a great variety of applications and also to a variety of solvers. And for this reason, they're the most common sort of modeling language. If you just say optimization modeling language, that's generally what people will assume that you mean. Okay? And so one approach, which I call the executable approach, is to write a computer program that resembles an optimization model and that can be executed to drive a solver. So the idea is to add to a programming language some additional objects and methods and such that you can use to write something inside the programs that resemble optimization models. And the declarative approach is to actually write a model description in a language that was specialized to look like a model description and that can be translated by a specialized solver to the solver's form. So to show the difference between these two, I'll go back to my example and I'll use a simpler set of data there. And for the executable approach, I'll use gurobipy, which is the gurobi solver's executable approach based on Python. And for the declarative approach, I'll use the AMPL modeling language, which also generates problems for gurobi and other solvers. And so let's go back to the mathematical formulation. There's the algebra. And I'm going to focus on these three sets and on the capacities. There's a capacity for every arc from every link in the arc set there. And so in gurobipy, which is the executable version, okay, we define this data by giving various Python lists and dictionaries. So you see there's a set of products, a set of nodes, and here's the set of arcs or links and the capacities. And in AMPL, that would look like this. This is the declarative approach. Here we just declare what these sets and parameters look like. In particular, we say that the capacities there's a capacity for every arc in the network. Okay, and then, but what happened to all this data that was here? Well, that goes somewhere else. That's provided later, and AMPL has a much stricter separation of the model and the data. And you see here, if you want to know what the capacity parameters look like, you basically have to look in the data to see that there's one for each pair of nodes in your network. Okay. Whereas in AMPL, there's actually an AMPL statement that tells you that there's a capacity for each arc. And then the arcs are somewhere, the actual arcs are somewhere in one of your data files. This is a text file, but there are other possibilities. So this makes it possible to validate the data much more strongly because you've stated exactly what it ought to be. And so then let's go on here and look at the model, and I'll focus on the variables and this second constraint here. Okay, this is again just the same as the model I showed earlier, and in Gurobi, you see that what we do is we have a function that applies to the products and the arcs data and is assigned to some flow variables, and then we can sum over those flow variables with a sum function. And so if you compare this constraint that we had to the way it's written in gurobipy, you see that there's a resemblance. The same terms show up, and the ones that are summations have a sum there, and so forth. And so it's very cleverly made to look in a way that's like this constraint. Okay, you do have to embed it inside a function call and so forth, but that's because it's Python. And here's how it would look in AMPL. And you see that in AMPL, it's possible to make it look a lot more like this constraint here. We can just say that flows are variables, because variables are a major kind of object in AMPL, as are constraints. And we can say if it's going to say some ij and a x pij, well, here's some ij and arcs flow pij. I've just given nicer names to the variables, that's all. And so there's a closer correspondence that I can make because I'm using a language designed for modeling. And so then we can run this here and get some results. And similarly in AMPL, I can run this here and do a solve and get some results. And I have a simple way of displaying them. I can even switch to another solver. But let's move on here and just compare executable, and one last comparison of the executable and declarative approaches. The main advantage of the executable approach is that you can do all your development in one language like Python or C++ or so forth. And it gives you sometimes also more direct access to advanced solver features. On the other hand, Python or whatever was not designed for describing models, and so constraint descriptions can be sort of awkward. You've seen the mixture of model and data. You may need some special methods. There are actually 3 ways of doing sums in gurobipy, depending on the efficiency you need. And then it can be hard to determine sometimes whether your bugs are due to the model or the program. And for the declarative approach, the main disadvantage of using something like AMPL is, well, you have another system. It's between the application and the solver. So you have to be willing to use a specialized system for that purpose. Okay? But the advantage you then get is that you have a system that's focused on optimization modeling. It streamlines the application prototyping, and it tends to be faster in processing. It gives the stronger validation that I mentioned because it says exactly what the data should look like, and easier maintenance because it's easier to read. And additionally, it's not specific to one programming language. So AMPL has its own scripting language to do some easy sorts of programming around the model. And then there are APIs for all the popular languages. So there's a Python API, but if you're doing it in C++, there's a C++ API. So you're not limited to one. And now that I've sort of gone through the different stages here and focused down on AMPL as a modeling language for optimization, I want to briefly describe some case studies. And in each case, there'll be 3 slides, one for the application that we're trying to do, one for the evaluation of how to approach it, and one for the implementation. And I'll go over these quickly, but hopefully give you a little feel for what's involved. So the first one is Young's Plant Farm, and they had their setting is that they grow many kinds of plants, which they ship to large retailers, and they have to, in order to ship them, they have to pack them into these huge racks. And their goal is to generate good packing plans for a day's orders and finish in time to get the orders out that day. They considered doing a spreadsheet, but settled on using an algebraic modeling language plus a solver. And they found that AMPL not only got them dramatically better solutions, but numerous economies, not only faster solutions using fewer people, but also better loading of racks and fewer trucks required. And they could choose from a selection of solvers. And the original model, and this, you'll see this in a lot of cases, the original model was built with help from a professor at a local university, but then the staff of the client took it over and extended it to handle larger orders. In this case, we helped them out some and implemented it. These problems are very large, as you can see, and they take 10 to 45 minutes to solve. But given that they're done on sort of a daily basis, that's enough. And they still use a spreadsheet for data prep and reporting results, but one specialist sits there and uses this optimization tool multiple times a day to actually get the solution out. So the next case is quite different. It's a design optimization case. And here we have a company that develops and sells electric flying vehicles, such as drones for various applications, possibly more ambitious vehicles. And they want to create a new electronic aircraft, which they can evaluate over many possibilities. So basically, they want to look at the optimal design in many situations in order to decide what to do. And so they considered a number of things, and including a design optimization system, which was Python based. But in the end, they chose to use an algebraic modeling language plus a nonlinear solver. And the reasons were in part that by using AMPL, they were able to implement complex physics equations using a formal model of optimization. It gave them the best results within a reasonable time frame. They could try various solvers, and then they could deploy via the API to embed this into their larger testing system. And the implementation, again, it was suggested by a professor at a local university, but it was implemented by 2 analysts at Motion Robotics. And it only took months to implement a first 1D prototype, which then encouraged them to expand to larger 2D models. And it takes not that much time for a solve, given the preferred solver. And they used the AMPL built-in scripting language for the core application, but then to connect it to other parts of their operation, they used the Python API. And they do huge number of runs on a compute cluster and have connections to other analytics and scientific software. So the third one is somewhat different from the other two in that our customer here is not actually solving the problem for themselves, but they're producing a product which they will then sell to other people. So ABB produces this product called GridView, which then performs optimization for a variety of customers that have a power grid application. So the situation is that there are two kinds of decisions basically in electrical service. There's when to turn power plants on and off, that's called unit commitment, and there's how to transmit power over the grid to meet the demand. And the goal in this case was to support planning, expansion, plan addition, retirement, integration of different energy sources, support that kind of planning by producing optimal decisions in a broad range of scenarios. So the idea is that the planners have to decide, well, would they want to do one thing or another and in what time frame? And to do that, they need to be able to look at what the optimal decision would be in each of these cases. So ABB considered doing the entire GridView system in C++, but in the end decided to use a modeling language for the optimization and the C++ only for the user interfaces. And this was partially for ease of modeling. Using AMPL, they could formulate complex models, and then customers could understand these formulations. And in talking to customers, they could show them how to specialize models even to their particular situations. And then it was using the AMPL C++ API, they could still embed the optimization part of it into the larger GridView system. And so the implementation, again, the prototype was done at the local university, but then 3 analysts at ABB took the project over and did a full AMPL implementation. This is a mixed integer problem that has millions of variables, tens of thousands of them integer, but takes them only about 10 minutes to solve. And it's been deployed to over 30 customer companies and has hundreds of customer side users of the application. Finally, a more topical example. This is an application for a student assignment in the current situation. And the idea here is that in the state of New York, the public schools were closed in the spring of 2020 by the COVID-19 pandemic. But then when they wanted to reopen, they need to reopen in a certain limited way. They could only have a certain number of students in a classroom. And they had to offer what they call blended instruction, where students would be divided into cohorts who would each cohort would attend 1 to 3 days a week. And it was important to keep students together in these cohorts to confine any transmission of the virus that might occur. And so what they were looking for was a tool for making workable assignments. And the tool had to be usable in each school by the principal, that's the person in charge of the school, or by someone the principal designated on short notice. So they didn't have a long time to learn how to use this tool, but they had to be able to use it. And the idea was they could somehow put in data they already had and get a solution out. And there are a huge number of schools, tens of thousands, so they had to be able to support many simultaneous users. And instead of having each principal figure out how to do this, they settle on using an algebraic language plus an appropriate solver. And AMPL enabled very fast prototyping and development, flexibility of solver choice, and had a Python API for deployment in an easy to use web tool. The implementation was done by someone at an investment firm, Goldman Sachs, who was actually a former professor. And the actual model was completed in just a few days, and with some help from a student and from one of our experts, they were able to get the whole thing running. And the actual optimization has tens of thousands of variables, but it takes only 1 to 4 minutes to solve. And it's deployed in an easy to use web tool that helps with data input and result reporting. To run it, you just click a submit button. And then behind the scenes, there's the Python application. And to be able to run lots of these problems, we helped them build a configuration where a new container in Amazon Web Services is spawned each time someone submits a problem. And the whole thing was built in 2 weeks using the AMPL API. So I'd like to thank you for your attention. Uh, we'll have a virtual booth at the Informs meeting if you happen to be there. And otherwise, here's our contact information. We'd be glad to discuss any of this with you further.